Hello, good morning. My name is Henrique Fernandes. I'm from Federal University of Uberlândia in Brazil. I'm currently doing a postdoc at the Fraunhofer Institute for Non-Destructive Testing in Saarbrücken, Germany. And today I'm going to share with you some infrared thermography inspections to detect defects in aluminium-CFRP hybrid 3D structure. Our agenda today consists of a brief introduction, materials and methods, where I'm going to show you the sample, the techniques that we've employed to inspect the sample, and then I'm going to share you some results and draw some conclusions. CFRPs are widely used in several industries due to their excellent specific mechanical properties, such as stiffness, strength, relatively high temperature, and oxidation resistance. So they have been used for several decades now. And it's important to have reliable inspection techniques to detect and warn of faulty parts. And infrared thermography has been a valuable tool in this sense. It's been used to ensure quality of the samples manufactured with CFRPs. In this paper, a metal CFRP hybrid structure with a thermoplastic layer between the CFRP and the metal is inspected. This combination, aluminium and CFRP, interlinks the benefits of each material. The hybrid structure is lighter than comparable metal samples. However, it can be a lot cheaper than parts only made of CFRP. Another advantage of the hybrid structure is the prevention of corrosion due to the thermoplastic layer. The inspected sample, as mentioned before, has a 3D shape. The materials used to manufacture it by injection molding process are this PPA resin with 30% volume of glass fiber. This carbon fiber was used as reinforcement. The layup of the material is 0.90 plus minus 45 symmetrically. And the metal, the aluminum inlay, is a 3 millimeter thick aluminum alloy placed in this position here, as can be seen in the picture. And we also included Teflon tape in this part of the sample in order to induce some artificial defects. The technique used to inspect the sample is the classic post-thermography, and this is the setup to use in reflection mode, where you use the dual band infrared camera, which works in both mid-wave and long-wave infrared, capturing data in both spectra. The frame rate for each spectra is 384 by 288 pixels, and we also use a circular flash placed here in front of the camera around the lenses in order to heat up the sample that was placed in front of them. We acquired raw data from the camera, and then our radiometric calibration was performed in order to obtain irradiance values. To perform this calibration, we need to get homogeneous radiance at different temperatures. And so in order to do that, a black body radiation source was used. We acquired two images from this black body, and then we performed the calibration. Details of this technique was published in last year's conference. In 2018 conference. We also performed a geometric correction in order to account for camera lenses distortion and the shape of the sample. How it's done? We acquired images from a known target and then we calculate the values, internal parameters of the camera. Then we apply some matrix multiplication, and then we get the corrected image. Here we can see the results for the midwave images. We can see, if we look closely, that the edges of the sample, they appear to have some curvature, some curves, yeah. And then in the correct image, this curvature is attenuated, so it's less present. We can also observe here these pixels are brighter, but the values of the pixels were not changed. What happened here is that some pixel that was in the edge of the image maybe got out of the image due to the correction, and then it caused the MATLAB, the software used to display the image, to rescale the display values, but the values of the pixel remain the same. So with these images, radiometric corrected, hadrometric calibrated, and geometric corrected, we applied some image processing techniques. We use two classical ones that have been used for a time now: principal component thermography and partial least square thermography. Both techniques are described in the literature, so I'm not going to review them here. And then, to compare the defect detection in both techniques, we employed a signal-to-noise ratio analysis, where we considered the average value of the defect pixels minus the average value of a arbitrary sound area, and then we divide it by the standard deviation of the values in the same sound area. So here I show you some results of the processed images in the midwave infrared spectrum. Image A is the third EOF from the PCT, and image B is the second loading for the PLST. We can see here in the region where the Teflon tape is that we have several voids here that were detected in both regions. We also spot we separate some defects here, 1, 2, and 3 here, the red, blue, and yellow points that we're going to calculate the SNR values of them to compare both techniques. And here I'm showing you the results obtained with the long wave infrared for both PCT and PLST as well. We can see that the voids in the Teflon area are there. We can also see them here. And I would like also to point out some other defects that are seen in both in all the images as well. Here we have an area that we believe is a raising rich area, that it's caused during the injection molding process. And also here around the aluminum part, we can see some areas that we also believe to be problems with the fiber raising here during the injection molding process. So we calculate the SNR for the 3 pointed out voids in the Teflon tape area. And we can observe that PCT has been better, given it gave better results, higher SNR values. And we can also observe that for the long wave infrared, they perform a little better than the midwave in our experiments. To conclude today, I shared with you results from inspection of an aluminium-CFRP hybrid 3D sample inspected with post-thermography. We acquired cameras raw data, and then we performed radiometric calibration and a geometric correction in order to have the values as close as possible of what is happening on the scene. Treated data was then processed with two different ER processing techniques, namely PCT and PLST. In both techniques, we are able to detect voids and also raising rich areas. Finally, for the voids, we performed an SNR analysis, which indicate that for these experiments, long-wave infrared process with PCT produced better results. Next steps in our study include adding the 3D geometric model of the sample for better visualization of the defects detected in the 2D infrared image. So thank you for watching my video and for your time. And I would also like to thank the Alexander von Humboldt Foundation and the CAPES agency from Brazil for their support. If you have any questions, please contact me using my email or access my website. Thank you again and have a great day.